Imagine a sleek electric vehicle gliding silently through a pristine landscape. Zero emissions, pure innovation. That's the dream sold by countless billion-dollar ad campaigns. But what if that picturesque vision is hiding a colossal, deeply inconvenient truth? What if the journey to electric mobility isn't as clean as it seems? Pause those glossy commercials. Forget the whispering tires on utopian roads. We're about to expose the unspoken reality behind electric cars, venturing far beyond the polished showrooms and into the hidden cost structures that the industry rarely discusses. Because while EVs promise a future free from tailpipe emissions, the truth is, their environmental ledger starts long before they even roll off the factory floor. This isn't just about what doesn't come out of a pipe. It's about everything that goes into chair-making and powering these machines. Prepare to question everything you thought you knew about green transportation, as we delve into the gritty details and uncomfortable facts that make up the complete cradle-to-grave story of electric vehicle lifecycle emissions. Are we truly embracing sustainability, or just shifting the pollution problem to a different zip code on the global map? The answer will redefine your understanding of eco-friendly. Before an electric vehicle can silently cruise city streets, vast quantities of raw materials must be ripped from the earth. Think lithium batteries 100 times over. Each one requires cobalt, nickel, manganese, and especially lithium. These critical minerals are disproportionately sourced from regions like the Lithium Triangle in South America, the Congolese Cobalt Belt, and Indonesian nickel mines. The extraction methods aren't pretty. Lithium mining, for instance, often relies on brine evaporation, which demands massive quantities of water, up to 2,000 tons of water per ton of lithium, impacting freshwater supplies and indigenous communities in arid desert regions. Cobalt, essential for battery stability, is heavily concentrated in the Democratic Republic of Congo, infamous for its harsh labor conditions, including reports of child labor and devastating ecological consequences, like widespread deforestation and severe ground and water contamination. Nickel mining exacts its toll through vast open-pit operations and massive, solid waste production. These processes aren't just resource-intensive, they generate extensive atmospheric and land pollution, destroying pristine ecosystems and uprooting local populations. The clean energy transition exacts a heavy price at its source, presenting a formidable ethical and environmental dilemma for our global supply chains, and the very definition of green innovation. Even after the minerals are extracted, transformed, and refined, the journey is far from green. The manufacturing of electric vehicle components, especially the monumental battery packs, is incredibly energy intensive. Creating a single kilowatt-hour, kWh of battery capacity, can generate 50 to 150 kilograms of CO2 equivalent emissions, largely dependent on the energy mix used during production. Considering an average EV battery capacity ranges from 60 to 100 kilowatt-hours, you're looking at a carbon footprint equivalent to manufacturing 2.5 full-size diesel sedans the 4 times the EV turns a wheel. This is known as embodied emissions. These figures account for everything from smelting aluminum, processing steel, creating plastics, right down to the sophisticated chemical processes, converting raw materials into battery cells. Many of these superfactories are located in regions heavily reliant on fossil fuel electricity. So while your shiny new electric car might have zero tailpipe emissions, its initial carbon debt is significant, often higher than that of an equivalent gasoline car upon purchase. This hidden toll is a crucial part of the life cycle assessment and an often overlooked factor in the so-called clean shift to greener motoring. It means that an EV, despite its long-term benefits, starts with a considerable environmental deficit that takes years to negate. Your EV's environmental performance doesn't solely depend on how it's made, but critically on where its electricity comes from. This is the power source paradox. Is your charging station tapping into a renewable grid powered by solar and wind? Or is it drawing heavily from coal-fired power plants? The reality is, EV charging is only as clean as its energy source. In a country like Iceland, almost entirely powered by geothermal and hydro, an EV approaches true zero emissions. However, in regions where electricity largely comes from burning coal or natural gas, the emissions simply shift from the car's tailpipe to the power plant. This means a significant portion of an EV's operational emissions are actually generated upstream at a power facility, contributing to a different kind of carbon footprint, making a direct, apples-to-apples comparison challenging and often misleading with traditional ICE vehicles. Understanding your local energy mix is vital to assessing your EV's actual environmental impact, revealing just how dependent green transit solutions are on broad-scale grid decarbonization. What happens when an EV battery finally dies after a decade of service? This isn't just about extending range. It's a critical challenge at the other end of the EV lifecycle. We could soon face a mountain of discarded electric vehicle batteries, potentially millions of tons by 2040. If not managed properly, these powerful components, often containing toxic and flammable materials, could become an environmental time bomb. Traditional recycling methods for lithium-ion batteries are energy-intensive and often costly, struggling to economically reclaim all valuable elements at purity levels required for new batteries, leading to reduced efficiency and material waste. Early battery chemistries present even greater challenges compared to newer options. There's a push for second life applications, where used EV batteries are repurposed for stationary energy storage, crucial for renewable grids. But even this offers only a temporary reprieve before they eventually need recycling. The success of circular supply chains is vital here, determining whether we can unlock the potential urban mining of these materials or if EV battery waste will overburden our ecosystems in the decades to come. Will we achieve a genuine recycling revolution or build a silent environmental crisis with every electric car sold? The stakes are incredibly high. Let's cut through the myths with hard data. We've talked cradle to grave, now let's plot it on a graph. A landmark lifecycle emissions study compared a typical mid-sized EV with an equivalent gasoline-powered car across regions with different electrical grids. The results might surprise you. Even when accounting for higher manufacturing emissions, an EV operating on a clean grid achieves net zero tailpipe. In fact, significantly lower total emissions over its 150,000-mile lifetime compared to an internal combustion engine ICE vehicle. But change the grid. In very coal-dependent regions, the gap shrinks, and it takes longer for the EV's environmental repayment period to kick in. The numbers show that, yes, in almost all scenarios, an EV's environment eventually generates lower overall life cycle emissions than a comparable ICE vehicle, the key word being eventually. This highlights a critical truth, that while an EV is a step in the right direction, achieving true green transportation requires synchronized advancements across mining, manufacturing cleanup, power generation, and recycling sectors. It's not a silver bullet, but a critical component of a much larger puzzle proving battery sustainability isn't just a marketing slogan anymore. Despite the challenges, innovation is aggressively carving a path forward. The next generation of electric vehicles promises drastically improved sustainability. Enter solid-state batteries. These game-changing innovations could fundamentally alter the EV landscape, replacing liquid electrolytes with solid ceramics or polymers, boosting energy density, potentially shortening charge times, and notably, utilizing less rare earth materials while enhancing safety and shelf life. Simultaneously, the focus on circular supply chains is transforming raw material sourcing and waste management. Advanced hydrometallurgical and pyrometallurgical battery recycling processes are making it more efficient and economical to recover highly pure lithium, cobalt, and nickel from spent batteries, turning trash into treasure for manufacturing new cells. This dramatically reduces the need for virgin mining and positions these critical elements as a sustainable loop. Beyond the car, renewable charging networks are expanding at an unprecedented rate, converting clean power, from solar farms to urban hydro projects, directly into vehicle energy. Imagine your car powered by microgrids, your home by its retired battery, your local fleet powered entirely without combustion. These emerging solutions aren't just incremental improvements. They represent systemic shifts designed to close the sustainability gap, driving us towards genuinely cleaner transportation alternatives at scale. We've journeyed through the entire life cycle, from the Earth's raw veins to the hidden emissions of the assembly line, the complexities of our power grids, and the looming challenge of battery waste, finally arriving at the exciting horizon of next-gen technology and circularity protocols. The question now looms larger than ever. Will ambitious climate policies and breathtaking technological advancements be enough to relentlessly push past these hidden costs and close the sustainability gap? Can we transition away permanently from old methods? Or will the sheer scale of material demands, the environmental burdens of extraction, and remaining infrastructural gaps ultimately stall widespread EV adoption as the greenwashing claims falter under true life cycle scrutiny. Your perspective, now informed by the unvarnished facts, is crucial. The future of sustainable mobility isn't merely about buying an electric vehicle. It's about holding the global production cycle accountable, demanding innovation, and supporting policies that champion true environmental responsibility from snuck cradle to cradle. The answers ultimately lie within how swiftly we evolve our technologies, refine our policies, and collectively demand genuinely sustainable choices. What future will we power?